Hello, everyone. So for those of you who don't know me, I'm Seif from Atelier 10. I work as an environmental designer with a focus specifically in daylight. And so this is kind of like veering away from more of the technical details of Radiance and more going towards the application of Radiance within design. And so I'm going to be going through 3 different projects that we've worked at A10 with different architects and teams, and going through 3 different design challenges that we faced with 3 very different interior spaces, and showing how we use Radiance as kind of like a graphic as well as analytic tool to provide, some feedback for design iterations and changes throughout the process. So the first case study that I'll be talking about is enclosing a courtyard. I've kind of kept it ambiguous to what the title names are to avoid any NDA issues. So this is a project that is an existing courtyard between 3 different historic buildings. The project is on a university campus. And so the team was prompted with converting this courtyard into an enclosed space for students to use as a workspace. So there's going to be like a cafe, as well as tables for students to, work on their laptops in between sessions. And so there was a lot of considerations to, look at within this project. Mainly, will the students be able to see what they're working on their laptop when they're sitting in this space? And so visual comfort was a main driver for the design of this courtyard space. Another aspect of it is they wanted to introduce a lot of greenery. So this courtyard is cut off on all sides, so it doesn't have any access to views to nature. And so they wanted to add, a green wall on this new stack design that they have in this courtyard to ensure that they have some sort of connection to greenery within this space. And so there's kind of like these 2 conflicting ideas of wanting to manage direct sun for visual comfort, but also ensure that there's sufficient direct sun to ensure plant growth on this green wall. And so we started off by evaluating the baseline condition without a skylight to understand where across the courtyard are we seeing concern in terms of visual discomfort due to direct sun, as well as what times of year we're seeing potential visual discomfort risk. So this is an annual direct sun animation. I'm not going to go through this entire animation, but this essentially allowed us to see what times of year are the most concerning. And we found that the times of concern were, the morning to early afternoon hours of the summer, which makes sense, as well as the morning hours of the fall and spring. So you can see specifically in those top 2 images during the summer, there's a very high amount of direct sun exposure on that courtyard, and it's going to be very uncomfortable to work in a space like that. And so ultimately what we wanted to do is understand how we can, modify the shading design within the skylight to mitigate this potential visual discomfort risk. It was also helpful for the architect to understand which areas in the courtyard are receiving more annual sun exposure throughout the year. And so this is an annual sun exposure map, which was very useful for the architect to understand where to position the furniture within the courtyard, even after we design a shading design to mitigate this. And so to understand what times of year specifically are going to be of concern, this is going to change depending on where you are in the courtyard. And so we created overshadowing diagrams across 9 different points in the space. So 6 in the actual courtyard, and then they were considering having this occupiable terrace towards the eastern portion of the space. And so we added 3 points there to understand what times of year in each of these positions are going to be of concern. So using Radiance, we overlaid essentially a sun path for the specific climate over a perspective rendering of the space. And this essentially allowed us to understand, as you can see by that area highlighted in red, the times of year that are going to be of concern from each of these points. This is also useful for the architect to understand where on the skylight they would need to provide some shading through either, split on the glazing or increasing the depth of those glulam members to ensure visual comfort in each of these positions. And so we did this for each of the points. You can see that, for example, this first point has a pretty high amount of occupied hours with potential visual discomfort. Same goes for the second point. But then as you go towards the southern end of the courtyard, you get some shading from the buildings, and therefore there's less concern for visual discomfort. We did this across all of the points. And this is for the terrace. You can see that for the terrace, when you're closer to the southern portion, there's actually no direct sun, so no visual discomfort risk. at least from direct sun. And then the other points are getting some visual discomfort, but the terrace is not going to be a regularly occupied space, and therefore there wasn't a great concern from the terrace's perspective to provide shading. So it's very useful understanding, from each of these different positions, the sun path relative to that position. However, ultimately what the architects wanted to know was where on the skylight should we provide more shading? You can kind of infer it from these images, but it'd be very difficult. And so what I've done is I created a Python script that will essentially identify the locations on the skylight that have the highest risk of visual discomfort due to direct sun penetrating in that area. And so I essentially created this map of critical glazing zones that would require extra shading to make sure that the courtyard specifically is protected from any visual discomfort risk. Then there's the other aspect of this. We're talking about the occupants and their comfort, but we also wanted to ensure that there's enough daylight coming in for plant growth for the green wall. I do want to caveat this by saying that the green wall is ultimately going to have some artificial lighting to ensure that plant growth is sufficient, right? You can't just rely on the direct sun coming in. However, they wanted to see in the baseline condition before we add the skylight, where are we at with the current green wall design? Which areas of the green wall are going to receive more light? Which areas are not going to receive more light? So they know how to design that artificial lighting for plant growth. And so the metric that we use for this is the daily light integral, DLI, which essentially lets us know the total photosynthetically active radiation accumulated over 1 day for the plant. And so we have this, there's a bunch of different references online, but we have some data referring to the different types of plants and what level of DLI they would need in order to be healthy. So the one that was often used for green wall was ferns. So we use that as kind of just like a benchmark for, are we receiving enough direct sun on the green wall within the courtyard space? So we then did another annual sun exposure map, but then modified it to, apply to the scale for DLI. And we identified that, intuitively, the higher up that you go within the green wall, the more sufficient daylight you get for plant growth. The lower you go on the green wall, the less efficient daylight that you have. And so this helped the landscape architect, as well as the architect themselves, to design the green wall more on the upper end of the stack rather than focusing on the lower end, which they initially wanted to do. And then there's another aspect of this. If we're trying to provide shading for the occupants of the space for visual discomfort, we also want to ensure that we're not blocking useful daylight penetration for the green wall itself. And so using that same script that I developed, you can also identify which areas of the skylight would need to be more open to allow light to enter for that green wall. And then you kind of get these two different maps, right? One for the occupants, one for the green wall. And you can kind of see that when you overlay them, they don't intersect that much, which is very great news for us. Meaning that we can kind of focus the shading strategies that we want to explore on this lower eastern portion of the skylight, and then keep the northwestern portion more open for plant growth. And so how are we going to shade the skylight? There's many different options that we can explore. And so we presented this to the architect to understand what they were open to us exploring. So the one example is, utilizing frit as glare control. Another one is using the actual structural members as shading elements themselves, which was initially our preferred method for shading the space, but the architect was less open to that. There's also other techniques like dynamic strategies, like electrochromic glazing and dynamic shading, as well as other materials like aerogel and Ocrolux that will allow for shading the space. Ultimately, the architect was only open to frit. And so we wanted to understand how we can do frit in a meaningful way to provide shading for the space while still, keeping some sense of connection to views outdoors, as well as telling a story through the frit design itself. So we started off by just doing a general frit across the whole skylight, right? Just to understand what is the density of frit necessary in order to mitigate some visual discomfort concern. So we took a time with visual discomfort concern, which is March 21st at 11:30 a.m. And you can see that you really need a very high density of frit in order to mitigate the contrast between the sun patches and the surrounding floor that would ultimately cause like micro scale glare, right? And so that's something we'll convey to the architect. And as I mentioned, we don't want to just apply a frit everywhere and just block the whole point of the skylight, which is to bring light in and give some sense of connection to nature. So we wanted to explore a different option. And so we proposed to the architect, well, using the script that I created previously, we kind of already identified which area we want to shade more than other areas. So that can kind of be used to understand the frit density across the skylight. So you can see in the furthest right one, we have a highest frit density of 80% in the bottom right, and then a gradients from 80 to 60 to 40 as you go towards the area that you want to keep more open for the green wall. So you can see that this sort of mostly addresses the microscale glare concern for the space, while still providing the occupants with, some connection to the outdoors as well. Great. I guess maybe instead of questions at the end, I'll stop at everyone briefly if there's any questions before I move on to the next case study. Yeah. So there's a bunch of research that's done online. I think this one was from a lab at Purdue that we use as a reference. But if you consult directly with the landscape architect in your team, they typically know what the DLI that's necessary to achieve plant growth. But there's a bunch of different resources online for people doing smaller scale tests to understand the level of daylight necessary for this plants. And you can see that it's not one number specifically, it's more of a range. So there is a minimum acceptable quality. But in order for it to be fully healthy and have a high quality in terms of plant growth, you need to be in that red range. Some of them have wider ranges, some of them have much narrower ranges. Great. Okay. So the second case study has a very different program. So this is a museum auditorium. Some of you may actually recognize the space. This project is now public, so I can name it by name. It's the Boston Museum of Science. It is right on the Charles River, and it's facing, has a big glazed facade that's facing east, if I recall, both southeast and southwest. So we were kind of presented with a very difficult challenge of they wanted to use the space as an auditorium space with a screen for lectures or for presentations, while also keeping complete access to views outdoors and having a fully glazed facade. Those are kind of, contradictory. You want to maintain views in increased daylight, but then it could cause a very high risk of lack of screen visibility for the people sitting there. And so that was a challenge that we were presented with for this project. In addition to that, they also wanted to test whether or not they can do projections on the floor in front of the people sitting down. And so that's another completely different challenge for, making sure we're still getting daylight in the space, but making sure the projections are visible. So that was the design problem that we were presented with for this space. And the architect, before we were onboarded, was already on board with having a double skin facade. And so we wanted to test different shading options as a part of this double skin facade to understand what's the most effective way of maintaining daylight while maintaining visibility. So we ultimately decided to test 4 different shading options. The first is fixed blinds with fixed spacing. The next one is fabric shades, that's deployable, electrochromic glazing, as well as dynamic rotating Venetian blinds. So for each of these shading options, we started off by doing an annual solar profile angle plot to identify the times of year that would require supplemental shading or the different levels of deployment across the times of year. So specifically for these fixed blinds, you can see that 15% of the occupied hours still require interior supplemental shading. The way that we're determining when we require supplemental shading is when the direct sun is encroaching onto the seating and causing visibility issues. And so we determined that fixed blinds will not be effective due to this need for supplemental shading because they are going to be having events all day from 9 a.m. till even nighttime. Comparing that to something like fabric shades, you'll see that, depending on the time of day, we're going to have to deploy the fabric shades to a different height. And so 39% of occupied hours will have the fabric shades fully closed, which is not ideal for a space that's trying to maintain views and maintain a sense of daylight in the space. So again, we ultimately decided not to recommend these fabric shades. Electrochromic glazing is another one. So you can see that 78% of occupied hours is going to have the tint with the lowest visual light transmittance. And therefore, again, this was not desirable for the specific space. Also, the tint of the color of the electrochromic glazing kind of interfered with the program of the space. So that was not desirable from the client. And this is the final one that we ultimately recommended, which is dynamic Venetian blinds. So, you know, there's only 1% of the total occupied hours that's going to have the Venetian blinds completely closed, meaning the remaining 99% is going to have some resemblance of the view outdoors, and it's also going to ensure that daylight is still encroaching into the space at a meaningful level throughout different times of the day. And so we ultimately recommended dynamic Venetian blinds just looking at these annual solar profile angles. But then there's the other aspect, right, of, well, will you be able to see the screen with each of these different shading option designs? So we did test all of them, but to keep this presentation within the 30-minute limit, I'm just going to be looking at the Venetian blinds for now, and then doing a comparison at the end of all the different shading options. So we tested this as multiple times throughout the day. We started off at 9 a.m., and you can see that at this time, there's optimal levels of daylight. You get some access to the views, great screen visibility, and color rendering. This is when you start deploying those Venetian blinds at 12 p.m. There's still a great sense of daylight. The access to views becomes a little more limited, but you still get a sense of the views outdoors, which is very great. It's on the Charles River, which is very beautiful. And we still get good color rendering in this case. This is at 1:30 p.m. during the winter. Again, very similar conditions. Get a sense of the view, get optimal daylight. Optimal daylight, and as well as good screen visibility. And then this is with an overcast sky where you wouldn't require the dynamic blinds to be deployed, and therefore there's optimal conditions in all cases, but not optimal daylight since it's overcast sky. And this is a helpful graphic to compare why we ultimately fully committed on the Venetian blinds that are dynamic, is because of, if you look at all the metrics comparing it at this time, which is 1:30 during the winter, which was a time of concern, you can see that the dynamic Venetian blinds is performing better than the other ones. So that's the screen visibility test that we did in terms of the shading design. Ultimately, we did go with dynamic Venetian blinds, and then we were presented with this extra challenge of like, okay, well, now we have these Venetian blinds. Can we have projections on the floor and have them visible? This is a bit more difficult, as you know, because it's much easier to get a higher brightness with a screen than it is with a projector, especially because of the distance that the projector is going to be from the ground. And so we wanted to evaluate would the projector specification that the architect provided to us be sufficient for projecting images onto the floor. And so we tested this small little 10-meter squared area, and we tested a viewpoint that puts the glazing as well as the projection area within the same field of view, because that's going to have the quote-unquote worst-case condition in terms of visibility of the projection. This was just us communicating to the architect about what is required in order to see this projection clearly. So we would require a high contrast between the display screen and the adjacent surfaces, with the brighter surface being the projection. These were the assumptions that we made. So the projector had a brightness at 22,500 lumens, and we assumed that the architect was going to be using a Marley mat to project onto. And so they were curious about whether they should go for a lighter Marley mat or a darker one, so gray or black, right? The answer is pretty straightforward, right? Which you can assume, but we presented that to them as a comparison using Radiance. And then the ultimate thing in this study is to identify what the brightness of the projection is going to be at the floor surface. And so this depends on a lot of factors, which is the brightness of the projector, obviously, but also the height of the projector above the mat. So it was located 20 feet above the mat and had an apex angle, which is just the projector's angle to the edge of the Marley mat, of 75 degrees. So these are the results. So this is projecting an example image that the architect provided to us on a gray Marley mat. You can see that the projection on the gray Marley mat has slight compromised visibility due to the high levels of ambient daylight. You can see that contrast between the projected image and the floor right adjacent to it is only 2-to-1, meaning that there's going to be very, or like a higher risk of lack of visibility of the projection. And this is the black Marley mat. Obviously, since it has much lower reflectance, it's not going to be as visible as when you use a gray Marley mat in this condition. And so we kind of wanted to convey to them, well, what are the different factors that are going to influence projection visibility? One is the reflectance, and you can see that the higher the reflectance of the mat, the greater the brightness of the projected image is. The other is obviously, the projector brightness. So we tested a brighter projector at 40,000 lumens, and the luminance ratio increased from 2:1 to 4.5:1, which helped with visibility, but ultimately we deferred to the AV consultant to determine whether or not this is sufficient for the needs of the space. Another thing is the ambient light level at the floor. And so obviously, again, the lower the ambient light level of the floor, the higher the contrast between the projected image and the floor, which will in turn improve the visibility of the projected image. And then a very simple thing is just moving the Marley mat. Having the Marley mat much closer to the glazing is going to increase the risk for lack of visibility for the projection in that space. So we suggested that they move that location closer to the northern side of the floor plate that's more distant from the glazing. Great. Any questions on that one? Mm-hmm. 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 I see. Okay, so the first question was back there. So the color rendering was more subjective. So this was like in coordination with the architect to understand, like, is this color rendering sufficient for the architect themselves? We didn't use a specific metric. It was just more subjective to more comparative between the different options that we had. And the reason why, for the second question, the reason why we use the contrast between the projected image and the surrounding and the ambient light level at the floor itself is to understand within the field of view that we have, is the luminance ratio going to be sufficient to have the projection visible, right? And so a big part of that is going to be the immediate connection between the luminance of the Marley mat or the projection on the Marley mat and the surrounding floor. So we saw that when they were more similar, the projection was much less visible, and when they were less, when there was a higher contrast, it was more visible. So we can go into the weeds like you're saying, but this specifically was just an easier way to communicate with the architect how you want to improve visibility of the projection. Yep.
I think like from the rendering that a really high vector will probably end up additional problems in the detail. Even if there is a concept.
Yeah. 100%. And that's something that we communicated with the architect. Like, this isn't the solution to making it completely visible. And it's understanding that when you have a bright background, like you're saying, with a lot of light coming in, ultimately you're going to have visibility issues. And, you can keep increasing the brightness of the projector. You can keep doing all these different things, but daylight is just going to limit visibility. And they understood that. So they were addressed that by having, the option for blackout shades when they want to ensure that the projections are very visible. But they were more so interested in just having general graphics like this projected onto the walls and the edges of the floor to give more of an ambiance in the space, less so to provide informative information. So they weren't concerned about having it very, very crisp. Yeah. Great. Okay. The last case study. So the last case study is looking at a very specific scenario in a theater space. So once again, I created a diagrammatic understanding of what the floor plan looks like for this space. And this space had, multiple different programs. It had a casino, it had a cinema room, but the main concern that we had with the space was they had this very bright entrance lobby for where people were going to be entering and exiting out of, that has glazing facing, southwest. And so they wanted to understand that when someone is transitioning from this entrance lobby into a darker vestibule, into a pre-theater lobby, is there going to be concerns with eye adaptation when you, move from one area to the other, and also vice versa, right? Like if you're going from a very dark space into a bright space, you might get that like sudden glare as a result of that. And so we use Radiance in order to determine if this is going to be a concern for the space. So starting off with the transition from bright to dark, we took four different viewpoints as you start entering this pre-theater lobby. And these are the luminance renders before we implemented eye adaptation. So we kind of wanted to convey to the architect that, yes, eye adaptation is going to be a big factor for causing glare, but there's also, before we implement that, a risk of glare due to, contrast between luminance in the field of view. In this case, not too bad. But when you start to implement the eye adaptation for this, you can start to see that effect of the vestibule becoming very dark within the field of view because the person is in a bright space. And so this is something that was not a concern in terms of glare, but more so in terms of the experience of transitioning through this space. And the way that we implemented this eye adaptation is using the histograms of the previous view for the next rendering, similar to how like the eye would adjust. And so ultimately, this was a very early stage analysis. And so they just wanted to understand, like, what are some quick fixes that we can do to improve this? And so the very obvious one is within the field of view, the bottom of the stair was very dark, which was causing this contrast. And therefore, we recommended a brighter or even luminous stair to reduce that contrast between the surfaces in the field of view. And also a very subtle thing that we can do is the vestibules currently are punch outs within the wall. And so just chamfering those edges will allow a softer transition between bright and dark. And then there's the other direction, which we predicted that would have a higher risk of visual discomfort due to transitioning from a dark space into a very, very bright space. So this is without adaptation. And this kind of goes to my point previously, where even without adaptation, due to the contrast and luminance within the field of view, we're still seeing some visual discomfort, even if the eye is fully adapted to that space. But once we implement the eye adaptation, then you see that visual discomfort is much more amplified because the eye is used to being in that dark space and then going to a bright one, so it's much more amplified when they walk into it. Again, we then suggested very simple recommendations as like the vestibule walls were very dark in terms of reflectance, so we asked them to increase it as one method. The other method, which is similar to the previous recommendation, is to just increase the reflectance of the bottom of the stair, because that seems to be a common theme in creating a contrast between surfaces within the field of view in either direction. Great. That is my presentation. Yep. Mm-hmm. Yes. Oh, no, sorry. For the DLI specifically, so that's a very great point. So this was before they even had any skylight design when we did that green wall, right? And so something to consider is like you're going to have very different, like to that point, you're going to have very different conditions when you have glazing, and the DLI is going to significantly reduce when you introduce the glazing. And so that's why I kind of hinted to the idea of like, regardless of how open we keep that section, they're ultimately going to require artificial light. But it just gives them a sense of where they can position the green wall to have to influence the artificial lighting design and minimize the amount of lighting that they would need. So yeah, like ultimately later in a later phase, because this was in, I think it was in SD, like the study that we did. When we were in DD, we started evaluating whether or not with the glazing, the DLI is going to be sufficient, and it wasn't. So that's a great point. Mm-hmm. Yeah. Yes. Yeah, no, that's a great question. So if I go back to that rendering quickly. So this was the original grid that they introduced for the structure. So we did model the structure to answer your question. But they did ultimately decide to change the pattern, and that kind of determined the reason why they were only open to using frit. So they, instead of having a much more dense pattern like this, they made it much more open, and therefore the structural members would have to go really low in order to shade it without using any glazing treatment, right? And so that's why they decided to ultimately go with the glazing treatment, even if it sacrificed some aspect of the views. No. Yeah. I think they introduced a green wall in a different portion of the project, but it just had to rely on artificial lighting to, influence plant growth. But that was more of like a VE decision, less so a daily decision.
Check, no concern for those very high contrast shadow light patterns that were moving across the floor.
That's a great question. So we did bring that up to them. We said that as a result of the design of the structure, like you're saying, there's going to be very, very weird sun patterns falling, especially on like the work surfaces when someone's working. That could be very distracting. And their response to that was like that was kind of like the appeal of the space. It kind of like added some character to that space, right? But a way that they addressed it as well is by increasing the grid size, so making those sun patterns a bit bigger and less densified. If that makes sense. Oh, yeah. Yeah. So you're talking about this project, right? Like the extra chromic? Oh, there. Okay. Yeah. So this was dependent on the level of or the depth of sun penetration, right? So like once the sun penetration was going deeper into the space, you would go with the highest tint level. If it was not that deep, then it would go the lower tint level, etc. And I think we forget which product we use as a reference, but we use the product as a reference for when these tint states are activated, depending on the amount of light coming in. Uh, you're saying, did I run it for a specific viewpoint? Or this one specifically, we ran for not a specific viewpoint, but a specific like area. So like we basically took like our analysis area to be where the seating is, and that determined, that was like the analysis area that determined the level of tint. So yeah. Sorry, could you repeat that? Yeah, I think that was brought into discussion, but I think the bigger concern was just like in general the use of electrochromic glazing for the space because of the tint in general, even with the parametric tint, because they felt that it was a bit disruptive to the program, and they also wanted to ensure that even when we are providing shading, we're still keeping access to the view across the whole glazing, and so they were more open to the idea of having those Venetian blinds that are more consistent in terms of the views. So it was in discussion, but ultimately they just decided to like forgo the idea of electrochromic glazing for this project. Cool. Thank you.